Thanks for the invitation from the organizing community. It's an honor for me to be here and present our work. Firstly, I will introduce myself. My name is Hongyuan Chuai. I obtained my PhD from Nankai University in 2019, where I mainly focus on head formulation. From 2016 to 2018, I was supported by the China Scholarship Council to study in France under the guidance of Rodolphe Clahac at CRPP-CNRS, where I mainly research on spin crossover complexes. In 2020, I joined Tianjin University as a postdoc researcher and began to explore electrocatalysis. Since 2024, I have been a research fellow at the Hongyuan Polytechnic University. Currently, I focus on the investigation of carbon sources utilization. Today, I will present the recent progress on and new discoveries in our research on the electrocatalysis. The content of my presentation today mainly includes copper-based catalysts for electrocatalytic reduction of CO2, carbon-based electrodes for CO2 electrode reduction, and the discovery of the carbon reduction reaction. As modern society rapidly advances, the overuse of fossil fuels has led to excessive carbon dioxide emissions and caused a series of climate and environmental problems. To address global climate change, the Paris Agreement was officially implemented in 2016. To achieve carbon neutrality, it is urgent to develop CCUS technologies. Compared to CO2 capture and storage, the electrochemical conversion of CO2 driven by renewable electricity can produce high value-added fuels and chemicals under mild conditions, achieving both low carbon emission reduction and the resource utilization of CO2. The products of CO2 electron reduction are complex, and the formation of C2 products involves multi-electron transfer processes, generally resulting in low Faraday efficiencies. To achieve the high selectivity preparation of a single product, identifying the active sites for C1 or C2 products is crucial. On the other hand, C1 products involves a 2-electron transfer process with a simple reaction pathway. Currently, the Faraday efficiency for CO and formic acid can both more than 90%, making the large-scale production of CO from CO2 feasible. In the first part of our work, in order to obtain C2 products with higher selectivity, we studied and analyzed the active sites for C1 and C2 products on copper-based catalysts. We prepared pure copper oxide and tin-modified copper oxide nanoparticles using a simple Sozhou method. XRD data showed that tin did not dope into the copper oxide lattice, and tin may be highly dispersed on the surface of copper oxide. SEM images reveal that pure copper oxide formed uniform particles, while tin-modified copper oxide aggregated into block-like structures. From the electrocatalytic performance diagram, it can be seen that copper oxide primarily produces C2 products, such as ethylene and ethanol, achieving a total Faraday efficiency of 54% at minus 1.5 volts with RHE. In contrast, tin-modified copper oxide mainly produces CO, with a CO Faraday efficiency reaching 61% at minus 1.1 volts with RHE. To confirm the active sites for C1 and C2 products, we used in situ Raman spectra to analyze the structural evolution and reaction intermediates of copper oxide and tin-modified copper oxide during CO2 electrolysis. As we can see in the figure, both copper oxide and tin-modified copper oxide were reduced to lower valent copper, which is further conversed by Chuai. In tin-modified copper oxide, intermediates such as bicarbonate, CO, and OCO, which are prone to CO formation, were detected. DFT calculations show that the adsorption of CO is much weaker on the tin-modified copper oxide surface compared to pure copper oxide, suggesting the enhanced performance of tin-modified copper oxide for CO production. When tin atoms are introduced into copper oxide, the free energy barrier of CHO increases significantly, suppressing ethylene production. Thus, the above results demonstrate that product selectivity can be tuned by introducing tin atoms. As we mentioned before, from the perspective of product selectivity, CO2 conversion to CO in scale is feasible. However, it also faces a significant challenge. The preparation of large-scale electrode for industry is difficult, and the stability of scale-up experiments is poor. Currently, electrocatalysis are mainly in powder form, prepared into electrode through traditional coating process, which can lead to catalyst detachment during long-term operation. To address these issues, we considered anchoring highly efficient CO-producing active sites such as nickel-nitrogen structures on carbon-based electrode and developed a technology for preparing large-scale carbon-based electrode via electrospinning. This part of our work is to regulate the pore structure of carbon-based electrodes to optimize their performance. At first, we introduced an organic pore-forming agent, PMMA, and nickel-doped ZF8 as a nickel source into the precursor, PAN sol-gel. After electrospinning and high-temperature calcination, we obtained the self-supported carbon-based electrode with nickel-nitrogen active sites. From the SEM images, we can clearly see that during high-temperature calcination, PMMA completely decomposed, forming open-ended through pores in the carbon fibers. XRD and Roman results showed that the addition of PMMA did not significantly affect the structure and disorder of the carbon-based electrode. XPS results indicated that nickel single atoms were anchored in the carbon fiber in a nickel-nitrogen coordination structure. In an H-cell, we performed CO2 electrocatalysis tests. The results showed that the electrode with the optimal PMMA addition, nickel PCNF points from PMMA, maintains a CO Friday efficiency of more than 90% within the potential range of -1.1 to -2.1 volts was RHE, and showed good CO Friday efficiency during 24-hour test. Then, we used potassium chloride as a pore-forming agent, PVP as a carbon and nitrogen source, and nickel nitrate as a nickel source to prepare self-supported carbon-based electrode with mesoporous structure, compared to the high molecular weight PMMA, which melts to form open-ended tubular through pores. The melting of the small molecule in organic pore-forming agent, potassium chloride, resulted in a more abundant dot-like pores on the surface of the carbon fibers. This not only promotes CO2 mass transfer, but also exposes more nickel-nitrogen carbon active sites. And then, We tested their electrocatalytic CO2 reduction performance in an H cell. The results showed that the optimized electrode, potassium nickel nitrogen, achieved a CO Friday efficiency of more than 90% within a wider electrochemical window, and maintained a CO Friday efficiency of more than 90% during 30-hour test. To further optimize the performance of carbon-based electrode, we added melamine as a performing agent to the precursor to prepare carbon-based electrode with microporous structure, and in this work, we discovered a novel carbon reduction reaction. As shown in the figure, melamine completely decomposed during pre-oxidation, resulting in a surface covered with micropores on the carbon fibers, with a specific surface area as high as 862 square meters per gram. We tested the performance of this electrode in an H cell. The electrode maintained a CO Friday efficiency of more than 90% over a potential of range of -1 to -222 volts, and showed a CO Friday efficiency of more than 80% during a 100-hour stability test, which is better than most reported powder catalysts with metal nitrogen structures in the literature. However, under industrial conditions, the Kant density is usually greater than 100 mA per square centimeter. To evaluate the performance of our prepared carbon-based electrode under working conditions, we conducted flow cell tests. The results showed that within the potential range of -1 to -1.8 volts, the CO Friday efficiency was less than 20%, and almost no hydrogen was detected. So we think there might be some liquid products generated, but NMR tests did not detect any common liquid phase products, such as formic acid, methanol, or ethanol. We hypothesize that long-chain organic compounds may have been produced, which are insoluble in heavy water. To collect the liquid phase products, we performed electrolysis at -1.8 volts for 160 hours. By extracting the electrolyte after the reaction, we obtained the white powder-like product shown in the round bottom flask. Pyrolysis mass spectral results showed that the main component of the product was long-chain alkenes. Among these, C18 was the dominant component, reaching a selectivity of 40%. To verify whether the obtained long-chain hydrocarbons were products of CO2 or not, we conducted experiments under the same conditions in argon and obtained similar white products. The white product in a blue-capped bottle was obtained from the electrolyte. This result indicated that the long-chain hydrocarbons were not the products of CO2 reduction. They are the products of the hydrogenation of carbon-based electrode. The above results demonstrate that carbon materials can undergo carbon reduction reaction under ambient temperature and pressure to produce high carbon products. In order to investigate the carbon reduction reaction, we characterized the carbon-based electrode before and after electrolysis, We can see from the SEM images that carbon fibers break into nanoparticles after electrolysis. To analyze the mechanism of the carbon reduction reaction, we used in situ infrared spectra to monitor the intermediates generated during electrolysis. The results revealed the peak of carbon-hydrogen bond, carbon-carbon double bond, CO, COOH, OH, and other intermediates. Based on the above experiment results, we proposed the mechanism of the carbon reduction reaction. Graphic carbon exists in sp2 hybridization with delocalized pi bonds in addition to carbon-carbon delta bond. When graphic carbon is connected to the cathode, the carbon atoms carry a negative charge. Meantime, the hydrogen evolution reaction on the cathode produces a large number of active hydrogen species in the solution. The interaction between the negative charged carbon atoms and the active hydrogen species disrupts the delocalized pi bonds of graphic carbon, leading to the formation of high carbon products. DFT calculations show that graphic carbon has good hydrogen adsorption capability. The formation of carbon-hydrogen bonds is more favorable under electrolysis conditions. To verify the uniformity of the carbon reduction reaction, we performed electrolysis on biomass-derived carbon for 114 hours. After treated the electrolyte after electrolysis, we also obtained similar white products. The pyrolysis mass spectra indicated that the products were long-chain hydrocarbons with octadiene nitrile selectivity about 50%. Thermocatalytic reactions involving inorganic carbon compounds such as CO, CO2, and so on, almost always require high temperature, high pressure, and metal catalysts. However, using carbon as the carbon source and water as the hydrogen source, high carbon chemicals can be obtained under ambient temperature and pressure without catalysts. From my point of view, the discovery of carbon reduction reaction holds significant scientific and application value. It has pioneered the synthesis of high carbon chemicals under ambient conditions without metal catalysts, using carbon as the raw material. It has expanded organic synthesis methods, provided new strategies for constructing carbon-nitrogen, carbon-oxygen chemical bonds, and opens up new methods for constructing long-chain organic compounds from inorganic carbon sources. The discovery of carbon reduction reaction also makes artificial oil synthesis possible. As we know, petroleum, a non-renewable resource, will eventually be used up. Simulating the natural process of bioorganic oil to achieve artificial oil synthesis has significant application value. Through the carbon reduction reaction, it is possible to use carbon-containing waste, such as biomass and plastics, without relying on crude oil to obtain high carbon chemical raw materials. This provides new ideas and technological support for green chemistry and sustainable development, helping to promote the transformation and upgrading of the petrochemical industry. To summarize my presentation and share our future research goals. During electrolysis, the carbon skeleton of carbon-based electrode undergoes hydrogenation to form high carbon chemicals. The carbon reduction reaction was discovered and proposed for the first time, opening up a new route for the electroreforming of carbon materials to produce high carbon chemicals. In the future, we will conduct research on carbon chain growth and the bond cleavage mechanism to achieve controllable carbon chain growth. We will introduce heteroatoms such as oxygen, nitrogen, and so on, and develop new methods for synthesizing organic chemicals from inorganic carbon sources under ambient conditions. Also, we will develop an artificial oil synthesis device integrating electrolysis, high-temperature pyrolysis to achieve a technological revolution from biomass to fossil fuels. Finally, I would like to share the motto of PolyU: to learn and to apply for the benefit of mankind. If one's horizons are broad enough to all of humanity, then the difficulties and obstacles encountered on the scientific research will hardly be worth mentioning. It is a pleasure to present our work today, and I hope that it can inspire more researchers to study carbon reduction reaction. My presentation ends here. Thank you all.